Gravity holds every star, every planet, every atom of you in place. Scientists understand it well enough to land a probe on a comet 67 million miles away, yet gravity has completely broken every equation physicists have tried to write about how the universe works at its smallest scales. We have two perfect theories. They disagree with each other completely, and nobody knows why. Today we go inside the greatest unsolved mystery in all of science. From the moment Einstein rewrote the rules of space and time, to the place inside a black hole where physics stops existing, to a theory that says our universe might be a flat projection on an invisible wall. If you enjoy the journey, a like and subscribe means a lot. Now, prepare yourselves. We begin. Gravity is the reason you are sitting down right now. It holds the moon in its orbit. It keeps the oceans from floating into space. It pulled every cloud of dust and gas in the early universe into the stars and planets we see today. Gravity is everywhere. Gravity is constant, and for most of human history, we thought we understood it. We were wrong. Here is the problem. Physics has two rulebooks. One explains the very big, galaxies, planets, stars, black holes. The other explains the very small, atoms, electrons, the tiny particles that make up everything you can touch. Both rulebooks work. Both have been tested thousands of times. Both are the most accurate theories in the history of science. They cannot both be right. When physicists try to use both at the same time, the math explodes. The numbers shoot off to infinity. The equations produce answers so large they are meaningless. Every single attempt to combine these two perfect theories falls apart, and it falls apart because of one force. Gravity. The most familiar force in your life is the one force that refuses to play by any known rules. Every other force in nature has been explained, measured, and connected to the others. Scientists figured out how electricity and magnetism are really the same thing. They figured out how the force that holds atoms together connects to the force that makes stars burn. Those were enormous victories. Each one took decades. Each one earned Nobel Prizes. But gravity sits alone, separate, untouched, and the strange part is that gravity is laughably weak. A refrigerator magnet can pick up a paperclip. Think about what that means. That tiny magnet, stuck to a kitchen door, is pulling that piece of metal upward against the gravitational pull of the entire Earth. The whole planet is trying to drag that clip down, and a $2 magnet wins. Easily. Gravity is the weakest force in the universe by a distance that is almost impossible to put into words. It is 1 followed by 40 zeros times weaker than the electromagnetic force. If you wrote that number out on paper, it would not fit on this page. Scientists call this the hierarchy problem, and nobody has a satisfying answer for why gravity is so incredibly feeble while still being powerful enough to shape the cosmos. So we have a force that is almost impossibly weak, yet dominates everything at cosmic scales. We have two perfect theories that both describe it, and neither one works alongside the other. We have math that collapses into nonsense every time someone tries to combine them. Something is missing, something fundamental about the nature of reality that we have not figured out yet. This is not a small gap in our knowledge. Every other unsolved problem in physics lives inside one of the two rulebooks. Quantum gravity lives in the gap between them, and that gap might be hiding the deepest truth about what the universe actually is. Before we get to the cutting edge, we need to understand how we got here. Because the story of gravity is a story of two men, separated by 230 years, who each thought they had the final answer. The first one almost did. In the summer of 1686, Isaac Newton handed the world a formula. It was elegant. Simple. A handful of symbols that described exactly how two objects pull on each other depending on their mass and the distance between them. Drop a rock. The formula predicts where it lands. Aim a cannon. The formula predicts the arc. Point a telescope at Jupiter. The formula predicts where its moons will be tomorrow, next year, a century from now. It worked perfectly. For 200 years, it worked perfectly. Scientists used Newton's law to track comets and predict eclipses. Engineers used it to build bridges. Astronomers used it to discover planets that nobody had seen yet, just by noticing that other planets were wobbling slightly off course. The law of gravitation was so powerful that when a small error appeared in the orbit of Uranus in the mid-1800s, scientists did not blame the formula. They predicted an invisible planet must be pulling it off track. They pointed their telescopes at exactly the right patch of sky. There was Neptune, right where Newton's math said it had to be. The formula worked. Nobody asked why. And that was the quiet problem hiding underneath 2 centuries of success. Newton himself admitted it. He described the math with total confidence, but refused to explain the mechanism. In his own words, he offered no hypothesis for why gravity pulled. The apple falls, the moon orbits, the numbers check out. But what is actually happening between 2 objects separated by millions of miles of empty space? How does the Earth reach out across a vacuum and grab the moon? Newton had no answer. Nobody did. And for a long time, nobody cared, because the formula kept being right. Then in 1915, a young patent clerk turned physicist sat down and asked the question Newton had refused to answer. His name was Albert Einstein. He was 36 years old. And the answer he came up with did not just explain gravity. It rewrote what space and time actually are. But here is the thing that makes this story strange. Einstein's answer was more accurate than Newton's. It fixed tiny errors that Newton's formula could not explain. It predicted new things that nobody had imagined. And yet Einstein's theory, like Newton's before it, eventually hit a wall. A different wall. A harder one. Newton's law failed because it could not explain the why. Einstein's theory would fail because it cannot survive the small. To understand why, you need to understand what Einstein actually discovered. Because it is not what most people think. Gravity is not a pulling force. It is something far stranger. And the moment you understand it, the reason it breaks modern physics starts to make sense. Imagine laying a heavy bowling ball on a stretched rubber sheet. The sheet dips. It curves downward under the weight. Now roll a marble across that sheet. Instead of going in a straight line, the marble curves toward the bowling ball. It follows the slope of the dent. From above, it looks like the bowling ball is pulling the marble toward it. But nothing is pulling anything. The marble is just following the shape of the surface. Einstein said space works exactly like that, except in 3 dimensions instead of 2. Every massive object, every star, every planet, every person standing on Earth, bends the fabric of space around it. Other objects do not get pulled toward them by some invisible force. They simply follow the curves in space that those massive objects create. The Earth is not pulling you down. The Earth has bent the space around it so severely that the path of least resistance points toward the ground. This sounds like a minor change from Newton. It is a total revolution. Newton said gravity was a force that acted between objects across empty space. Einstein said gravity is the shape of space itself. Space is the force. The geometry is the engine. And what made this impossible to dismiss is that Einstein made predictions nobody had dared to make before. He said that if space bends, then light bends too. Light always travels in a straight line. But if space itself curves, then the straight line curves with it. A beam of light passing close to the sun should bend slightly toward it, following the dip in space the sun creates. In 1919, 4 years after Einstein published his theory, a team of scientists travelled to Africa and the Pacific to photograph a solar eclipse. The eclipse blocked the sun's glare and let them photograph stars that should have been hidden just behind the sun's edge. Those stars were visible. Their light had bent around the sun exactly as Einstein predicted. The whole world heard about it within days. Einstein became the most famous scientist on the planet overnight. His theory also predicted something Newton never imagined. Gravity slows time. An object in stronger gravity experiences time moving slightly slower than an object in weaker gravity. The closer you are to a massive object, the slower your clock ticks. This is real. Measurable, the satellites that power your phone's navigation system orbit high above Earth, where gravity is slightly weaker. Their clocks run slightly faster than clocks on the surface. Every single day, engineers must correct for this difference, or navigation systems would drift off by miles within hours. Einstein was right. Space curves. Time bends. Gravity is geometry. So we had Newton, who described gravity with a formula, then Einstein, who explained gravity as the shape of space. Both were triumphs. Both felt like final answers. And then physicists tried to zoom in. All the way in, down to the level of individual particles, down to the scale where atoms are not just small, but where the entire universe operates by completely different laws. That is where everything fell apart. Picture two instruction manuals for the same machine. One manual works perfectly for everything bigger than a grain of sand. The other works perfectly for everything smaller. Both manuals have been tested more rigorously than any document in human history. Both give correct answers millions of times a day, but when you open both manuals and try to follow them at the same time, the instructions are completely incompatible. That is exactly where physics stands today. General relativity, Einstein's theory, describes gravity as smooth curved space. The key word is smooth. Space in general relativity is a continuous fabric with no gaps, no graininess, no smallest piece. It stretches and bends the way water flows, seamlessly, in every direction at once. The math that powers general relativity requires this smoothness to function. Without it, the equations do not work. Quantum mechanics describes everything else: particles, energy, forces, the structure of atoms. The key feature of quantum mechanics is the opposite of smooth. Everything in quantum mechanics comes in chunks. Energy does not flow in a continuous stream, it arrives in discrete packets. Particles do not have a precise location until you measure them. The entire universe at the smallest scale is grainy, jumpy, and probabilistic. These two pictures of reality are mathematically incompatible. General relativity needs a fixed, smooth background of space to function. Quantum mechanics says that background is constantly flickering and vibrating. At the very smallest scales, space itself should be foaming and jumping violently, shredded by quantum energy. General relativity breaks down completely in that environment. Its smooth curves become meaningless in a universe of constant quantum chaos. Physicists discovered this conflict in the middle of the 20th century, shortly after the triumph of building quantum theory. They tried to apply the same techniques to gravity that worked so brilliantly for every other force. For the electromagnetic force, for the nuclear forces, the math was hard, but it worked. They expected gravity to be similar. The calculation came out as infinity. Every single approach produced infinite answers. Infinite energy. Infinite curvature. Infinities that could not be cleaned up or corrected. A theory that outputs infinity is a broken theory. You cannot build a bridge using a formula that gives you an infinite number of tons. Infinity is math's way of telling you something has gone wrong. And with gravity and quantum mechanics combined, infinity appeared everywhere they looked. They tried again. Different methods. Different starting assumptions. Still infinity. And here is what makes this genuinely frightening for physics. Every other infinity problem in quantum mechanics has been solved using a mathematical trick called renormalization. It works by absorbing the infinities into the definition of particle properties like mass and charge. It sounds like cheating, it is slightly like cheating, but it produces correct predictions, so physicists accepted it. With gravity, renormalization fails. The infinities in quantum gravity are a different kind. They cannot be absorbed. They multiply. Every attempt to remove one creates more. Two perfect theories. One universe. A mathematical disaster hiding at the boundary between them. And the disaster gets much worse once you understand exactly what these two theories are built on. Every atom in your body is held together by forces. The force that keeps electrons orbiting the nucleus. The force that holds the nucleus itself together against the pressure of all those packed positive charges trying to explode outward. The force that lets the sun burn by converting one type of particle into another. 3 invisible forces, working constantly at scales you cannot see, keeping the matter of the universe intact. Scientists spent the better part of the 20th century figuring out all 3. The result is called the Standard Model. The Standard Model is the most tested theory in all of science. It describes every particle ever discovered and 3 of the 4 fundamental forces of nature. It predicted the existence of particles decades before anyone could build a machine powerful enough to detect them. When those machines were finally built and those particles were found, they were exactly where the Standard Model said they would be. The precision is staggering. Some predictions have been confirmed to an accuracy of 1 part in a billion. The Standard Model works by describing forces as exchanges of particles. Every force has a carrier. The electromagnetic force is carried by photons, the particles of light. The strong nuclear force, which holds the nucleus together, is carried by particles called gluons. The weak nuclear force, responsible for radioactive decay, is carried by a 3rd family of particles. These force carriers are constantly being exchanged between matter particles, and those exchanges produce what we feel as forces. This picture of forces as particle exchanges is the foundation of quantum field theory. It is elegant, testable, and wildly accurate, and gravity fits nowhere inside it. Scientists have attempted to extend the Standard Model to include gravity. The force carrier for gravity would be a particle called the graviton. Theoretically, the graviton should exist. Every other force has a carrier, so gravity should too. The graviton would carry the gravitational force between objects, the same way photons carry the electromagnetic force between charged particles. The problem is not conceptual. The math itself breaks down. When physicists write the equations for a graviton inside the framework of the Standard Model, the infinities appear immediately. The theory becomes what physicists call non-renormalizable. The mathematics produces endless cascades of infinities that cannot be removed. Every other force carrier fits cleanly into the Standard Model. The graviton tears it apart. So the Standard Model sits as the most successful theory ever built, covering almost everything, and gravity stands outside it completely. The force you feel every second of your life. The force you have understood since childhood, the force that shaped every galaxy in the universe, is the one thing the most accurate scientific theory ever created cannot explain. Physicists have known this for decades. The problem has resisted every attack. And part of the reason gravity is so resistant is something deeply strange about its character. Something that bothers physicists more than almost anything else about the universe. Gravity is almost unbelievably, almost laughably, almost insultingly weak. And nobody knows why. Hold a paper clip above a table and let go. It falls. The entire mass of the Earth, 6 trillion kilograms of rock and iron and molten metal, is pulling that clip downward. The gravitational force of a whole planet is acting on that piece of metal right now. Now hold a refrigerator magnet near the same clip. The clip jumps up, a small painted piece of plastic and metal weighing almost nothing, just overpowered the gravitational pull of an entire planet. The magnet won, easily, without effort. That is how weak gravity is. Physicists have measured the difference between gravity and the electromagnetic force. The number is 1 followed by 40 zeros. Gravity is 1 followed by 40 zeros times weaker than electromagnetism. That gap is so enormous that ordinary language fails to describe it. The distance from Earth to the nearest star is about 25 trillion miles. Now imagine comparing that distance to the width of a single human hair. The ratio of the electromagnetic force to gravity is even more extreme than that comparison. Every other force in the universe, the electromagnetic force, the strong nuclear force, the weak nuclear force, they all operate in roughly the same ballpark of strength. They are not identical, but they are in the same conversation. Gravity is something else entirely. It is sitting alone, impossibly far below the others, operating at a strength that seems almost accidental. This gap is called the hierarchy problem, and it is one of the deepest unsolved puzzles in physics. Why are the forces so different in strength? If the laws of physics were slightly different, gravity might be powerful enough that no stable atoms could form, or it might be strong enough that the universe collapsed back on itself seconds after the Big Bang. The strength of gravity is precisely what it needs to be for a universe like ours to exist. That precision, that exact weakness, demands an explanation. The weakness also has a direct consequence for how hard it is to study gravity at small scales. Every experiment that has tested quantum mechanics used the other forces. Particle accelerators slam particles together using electromagnetic force. The resulting collisions reveal the structure of matter with extraordinary detail, but the gravitational pull between two subatomic particles is so vanishingly tiny that it is completely invisible to any instrument ever built. There is no experiment, no machine, no detection method that can measure the gravitational interaction between two electrons. Gravity simply vanishes at small scales. It gets swallowed by the noise of every other force around it. So the very scale where quantum mechanics operates is the same scale where gravity becomes effectively invisible. Physicists are trying to combine two theories whose domains barely overlap. One force rules the large and disappears at the small. One theory rules the small and cannot reach the large. The meeting point between them should be the key to understanding everything. That meeting point has a name. And what happens there is unlike anything else in science. Every force in nature has a messenger. When a magnet pulls a piece of iron, it is not magic. Photons, the particles of light, are constantly flying back and forth between charged objects, and those exchanges produce the electromagnetic force. You cannot see individual photons doing this, but the mathematics of quantum mechanics describes it precisely, and the predictions match every experiment. The strong nuclear force uses messenger particles called gluons. The weak nuclear force uses its own set of carriers. Every force in the standard model has its messenger particle, and each one has been detected in laboratories around the world. Gravity should have one too. Physicists call it the graviton. It would be massless, meaning it travels at the speed of light. It would have no electric charge, and it would carry the gravitational force between all massive objects, the same way photons carry the electromagnetic force between charged ones. The graviton has never been detected. No experiment in history has captured one. The reason is the same extreme weakness of gravity that we explored before. To detect a particle, you need to sense its effect. Photons are easy. A photon hits your eye and triggers a signal. Even single photons can be detected with modern equipment. Gluons are harder to see directly, but their effects appear clearly in particle collision experiments. A graviton from a single particle would produce an effect so tiny that detecting it is physically out of reach. Scientists calculated what it would take to build a detector sensitive enough to catch a single graviton from a particle accelerator. The detector would need to be so massive, so dense, so enormous, that it would collapse into a black hole under its own gravity before it could function. The universe itself seems to be preventing us from observing the particle that carries one of its own fundamental forces. The graviton sits in a strange position in physics. The mathematics suggests it must exist. Every other force has a carrier, and the structure of the theory points toward a graviton completing the picture. But the theory that would describe the graviton, quantum gravity, does not exist yet in a complete form. And with no working theory and no possible experiment, the graviton remains a prediction with no home. This matters beyond just finding one particle. If the graviton exists, and physicists could understand it fully, the theory that describes it would also be the theory that unifies general relativity and quantum mechanics. Finding the graviton would mean solving the biggest problem in physics. The graviton is the key. And the key is hidden somewhere beyond the reach of every tool we have. Some physicists wonder whether the graviton exists at all. If gravity is not actually a force in the quantum sense, if it emerges from something else entirely at larger scales, then the graviton might be a concept that makes no sense. But to know if that is true, physicists need to understand what happens at the smallest possible scale the universe allows. That scale has a name, and it is more extreme than anything you have imagined so far. The most powerful particle detector ever built sits beneath the border of France and Switzerland. It is a ring 27 miles in circumference. It uses thousands of superconducting magnets, each cooled to temperatures colder than outer space, to accelerate particles to 99.999% of the speed of light before smashing them together. The collisions release enough energy to recreate conditions from fractions of a second after the Big Bang. That machine cannot detect a graviton. A team of physicists worked out the math on what a graviton detector would actually require. They started with the fact that to detect a graviton, you need something massive enough to interact with gravity at the quantum level. The more massive your detector, the better your chance of catching a graviton signal, so you make it bigger and denser. But the moment your detector reaches a certain mass, it collapses into a black hole. Gravity turns the detector into the very thing that absorbs everything and lets nothing escape. Every design leads to the same outcome. Scale it up and it becomes a black hole. Keep it small and the graviton signal vanishes into background noise. There is no middle ground. The universe, in a deeply strange way, appears to have placed a hard wall between us and the direct observation of its own gravitational quantum. This is called the graviton detection problem, and it is unique in physics. For every other particle ever discovered, someone eventually found a way to see it. Sometimes it took decades. Sometimes it required machines the size of cities. But it was always physically possible, even if technically very hard. The graviton stands apart because the physics itself seems to forbid detection. Freeman Dyson, one of the great physicists of the 20th century, argued near the end of his life that the graviton might be permanently undetectable. His argument was careful and mathematical, and while many physicists dispute it, nobody has found a clean way to prove him wrong. If Dyson was right, it means we are trying to build a theory around a particle we can never observe directly. Physics becomes something closer to pure mathematics, where the only test is internal consistency and indirect agreement with things we can measure at larger scales. But physicists are not ready to give up. Because even if the graviton is invisible, the effects of quantum gravity should leave fingerprints. And the most extreme place those fingerprints might appear is inside the smallest distance the laws of physics allow to exist. A distance so tiny that sitting inside it, all of space itself would be shaking apart. Imagine cutting something in half, then in half again, and again. You get a grain of sand, then a bacterium, then a virus, then an atom, then the nucleus of an atom, then a proton. Keep going, keep cutting. Eventually you reach a scale where the very act of measuring a distance changes the space around you so violently that the measurement becomes meaningless. That scale is called the Planck length. The Planck length is roughly 600 billion trillion times smaller than a single proton. To even picture this, consider that a proton is already so small that you could line up 1 million of them across the width of a single human hair. Now take one of those protons and divide it into 600 billion trillion pieces. Each piece is roughly the size of the Planck length. Below this scale, the two rulebooks of physics do not just disagree. They both fail entirely. At the Planck length, quantum energy fluctuations become so violent that they warp space itself. General relativity describes space as a smooth, curved surface. At the Planck length, that surface is no longer smooth, it is foaming, it is shredding. The geometry of space becomes so distorted and chaotic that the mathematical tools of general relativity cannot function. And quantum mechanics, which thrives on the small, requires a stable background of space to make its calculations. At the Planck length, that stable background does not exist. Space itself is too unstable to use as a foundation. Both theories arrive at the same door and both are locked out. This scale was identified by physicist Max Planck in 1900, years before quantum mechanics or general relativity existed in their modern forms. Planck was working on a completely different problem, trying to understand how objects emit heat and light. He noticed that certain fundamental constants of nature, the speed of light, the gravitational constant, and his own newly discovered quantum constant, could be combined to produce a natural unit of length. He published the number almost as a curiosity. Decades later, physicists realized that Planck length was not just a curious calculation. It marks the boundary where all known physics stops working. It is the edge of the map. The terrifying part is what lies beyond it. At the Planck scale, space may stop being a continuous thing entirely. Space might be made of something. Discrete units. Chunks. A grainy structure at the very bottom of reality that our equations cannot yet describe. If space is not smooth all the way down, then everything built on the assumption that it is, which includes general relativity, needs to be rebuilt from scratch at that level. And there is one place in the observable universe where the Planck scale is not just a theoretical limit. One place where matter is crushed so completely that the Planck scale is reached for real, where the smooth fabric of space has been folded into a single point, and where everything we know breaks apart. What lives at that point makes the Planck length look like a simple problem. A black hole begins with a star many times larger than our Sun. When that star runs out of fuel, the fire holding it up goes out. The outer layers explode. The core collapses inward. In less than a second, something the size of a city crushes down to a point smaller than a proton. Gravity wins completely. Everything that was the core of a massive star gets compressed into an infinitely small, infinitely dense point, called a singularity. Singularity, the word itself, is physics admitting defeat. Understand what infinitely dense means. All the mass of that stellar core compressed into zero volume. Density is mass divided by volume. When volume reaches zero, density becomes infinite. Infinite curvature of space. Infinite gravity. Infinite everything. Infinity appearing in physics always means the theory is broken down. Infinity is an alarm. When you get infinite density, general relativity is telling you that it has reached the edge of what it can describe. The theory fails at the singularity. It produces an answer that cannot be physical. Space cannot actually curve infinitely. Time cannot actually stop completely. Something is happening that general relativity cannot capture. So physicists turn to quantum mechanics, because the singularity is also unimaginably small. The Planck scale and smaller. Quantum mechanics should take over at this size, but quantum mechanics requires a background of space to work in. At the singularity, space is not a background anymore. Space is the thing that has been destroyed. Quantum mechanics needs a stage, and the singularity has collapsed the stage. Both theories arrive at the center of a black hole. Both break down. Simultaneously, this is the one place in the universe where the collision between general relativity and quantum mechanics is guaranteed and unavoidable. You cannot look away from it. You cannot say it only matters at extreme scales far from everyday life. Every galaxy in the observable universe contains a supermassive black hole at its center. There are estimated to be hundreds of billions of black holes across the observable universe alone. Each one contains a singularity. Each singularity is a place where physics stops working. The universe is full of holes in our understanding. Literal holes. Stephen Hawking spent decades studying black holes precisely because they are where the two theories meet. He found something remarkable. He found that black holes are not entirely closed. They radiate, very slowly. a tiny thermal glow leaking away into space. He called it Hawking radiation. That discovery seemed like good news. A bridge between quantum mechanics and gravity, a real physical effect that required both theories to explain. But Hawking radiation did not solve the problem. It deepened it. It revealed a new crisis. A crisis that went right to the heart of whether information can survive inside a universe ruled by quantum mechanics. A crisis about what happens to everything that falls in. That crisis has its own name, and it has divided physicists for 50 years. When engineers design a bridge, they use equations. Those equations predict the stress on every beam, the load each cable carries, the vibration frequencies that could cause collapse. If any equation produces an answer of infinity, the design is wrong. Infinity means something broke in the calculation. Real bridges have real numbers. Physics works the same way. A theory that produces infinite answers is a broken theory. In the 1940s and 50s, physicists developed quantum field theory to describe particles and forces. Early versions produced infinities. The calculation for the energy of an electron, for example, kept giving infinite results. That was a problem, but physicists found a way through it. They developed renormalization. Renormalization works by recognizing that some infinities are artifacts of the math, not physical reality. You absorb the infinity into the definition of a measured quantity, like the mass or charge of a particle, and the rest of the calculation produces finite, meaningful numbers. It looks uncomfortable. It is uncomfortable. But it works. Renormalized quantum field theory makes predictions accurate to 1 part in a billion or better. When physicists applied this same approach to gravity, something different happened. The infinities in quantum gravity are not isolated. They are not one infinity hiding in one place that renormalization can absorb. Quantum gravity produces an infinite series of infinities. Every time you try to remove one, the calculation requires a new term with its own infinity. You remove that one, and another appears. Then another. You need an infinite number of measurements to fix an infinite number of infinities, which means the theory has infinite free parameters. A theory with infinite free parameters predicts nothing. You can tune the infinities to match any experimental result. A theory that can predict everything actually predicts nothing, because it places no constraint on reality. This is called a non-renormalizable theory, and quantum gravity, approached using the standard tools, is non-renormalizable. The math is not just hard. The math is structurally broken. Physicists spent decades trying different approaches. They tried starting from general relativity and adding quantum corrections, still non-renormalizable. They tried starting from quantum mechanics and building gravity in from scratch. The infinities came back in different forms. They tried reformulating the entire mathematical framework. Each attempt produced variations of the same structural failure. The problem is not technical. Physicists have solved technically brutal calculations before. The problem is that gravity and quantum mechanics seem to be built from fundamentally incompatible assumptions about what space and time are. General relativity treats space as something real and physical that bends. Quantum mechanics treats space as a fixed backdrop. Combining them is like trying to write a story where a character is both the author and the fictional setting simultaneously. The math reflects the conceptual impossibility, and when physicists dug deeper, they found that the failure of renormalization was pointing towards something specific. The infinities were appearing most catastrophically at one particular scale. The Planck scale. The same boundary where space itself breaks down. The math was screaming that the real answer lies somewhere beyond our current tools. Somewhere in a territory that none of the existing theories can reach. 2 major attempts have been made to build something that can reach there. Both are brilliant. Both are incomplete. Both have passionate defenders and fierce critics. The first one proposes that everything in the universe, every particle, every force, even the graviton, is made of something almost impossibly tiny and endlessly strange. Richard Feynman called it a shell game. He said it himself. Renormalization, the technique that rescued quantum field theory from its infinity problem, was a procedure that felt deeply uncomfortable to him. But he also helped invent it, and despite his discomfort it worked. Here is what renormalization actually does. When physicists calculate the properties of a particle, they have to account for all the quantum effects happening around it. An electron, for example, is constantly surrounded by a cloud of virtual particles popping in and out of existence. These virtual particles affect the electron's energy, its mass, its charge. When you try to calculate the total energy of an electron, including all those quantum effects, the sum keeps growing. Every layer of detail you add makes the number bigger. Add enough layers and the energy becomes infinite. Renormalization says, stop pretending you know the bare properties of the particle from first principles. Instead, define the particle's properties by what you actually measure in experiments. Absorb the infinity into that definition. The leftover mathematics, the part that describes how particles interact and scatter, comes out finite and correct. It is mathematically equivalent to subtracting one infinity from another to get a regular number. That sounds insane. Mathematicians would not accept it. But the answers are correct. Quantum field theory built on renormalization predicted the magnetic moment of the electron to 11 decimal places. It is the most accurate prediction in science. Physicists accepted renormalization because results matter. So when the time came to apply the same approach to gravity, they expected discomfort but anticipated success. The discomfort arrived as expected. The success never came. In quantum gravity, the interactions are different in structure. Each new layer of quantum effects does not just add a term to the calculation. Each new layer introduces an entirely new type of infinity with its own structure. A new infinity that requires its own new measurement to absorb it. And then that absorption introduces yet another infinity with another structure, requiring another measurement. It does not converge, it cascades. An infinite tower of distinct infinities, each one requiring its own fix, with no endpoint. To fully renormalize quantum gravity using standard techniques, you would need to perform an infinite number of measurements. Infinite measurements to define infinite parameters. A theory with infinite free parameters is a theory with no predictive power at all. It fits any observation by construction. Physicists realized this was not a technical problem to push through. The cascade of infinities was a structural signal. The theory was telling them that something deeper was wrong. The mathematical framework of standard quantum field theory was the wrong language for gravity. This forced a confrontation. If the standard tools do not work, physicists need new tools. New frameworks, new mathematical structures that can handle gravity at the quantum level. The search for those new tools produced some of the most ambitious ideas in the history of science. Ideas involving extra dimensions, vibrating strings, and the possibility that space itself is made of something other than nothing. One of those ideas suggested that every particle in the universe, including the graviton, is actually a tiny loop of vibrating energy. And that idea changed the direction of theoretical physics for 40 years. Time is not the same everywhere. This is not a thought experiment. It is not a theoretical curiosity. It is happening right now, to objects you rely on every single day. Einstein's theory of general relativity makes a specific prediction. Gravity affects time. The stronger the gravitational field, the slower time passes. An object deep in a gravitational well, sitting close to a massive body, experiences time moving more slowly than an object far away where gravity is weaker. The effect is tiny near Earth. But it is real. And it is measurable. Every time you use navigation on your phone, your location is calculated by signals from satellites orbiting roughly 12,000 miles above the surface. Those satellites carry extremely precise atomic clocks. They broadcast their time constantly, and your phone uses the tiny differences in when signals from different satellites arrive to calculate exactly where you are. The whole system depends on the satellite clocks staying perfectly in sync. Here is the problem. Those satellites are far from Earth, where gravity is weaker. According to general relativity, time at that altitude runs faster than on the surface. The difference is about 38 microseconds per day. That sounds tiny. It is not tiny. If the satellite clocks were left uncorrected, that 38 microseconds of drift would cause navigation systems to be off by roughly 7 miles in a single day. The error would grow every day. Maps and navigation would become useless within weeks. Engineers account for this by programming the satellite clocks to run slightly slow before launch, so that gravitational time dilation brings them back into sync with Earth. Every satellite in the navigation system is carrying a built-in correction for Einstein's theory. The practical proof of gravitational time dilation is sitting above your head in orbit right now. But the deeper implication of time dilation is what makes it relevant to our story. If gravity bends time, then at the most extreme gravitational fields in the universe, time does not just slow, it approaches a complete stop. Near the event horizon of a black hole, the boundary past which nothing can escape, time slows dramatically from the perspective of a distant observer. An astronaut falling toward a black hole would, from the outside, appear to slow down as they approached the horizon. They would seem to hang there, frozen at the edge, their image fading and reddening as light struggled to escape the gravity. From the astronaut's own perspective, time would flow normally. They would cross the horizon and continue inward. But what continues inward leads to the singularity, and at the singularity, time itself ends. Space and time are not just warped by gravity. At the extreme, they are destroyed by it. This complete destruction of the space and time framework is exactly why quantum mechanics fails at the singularity. Quantum mechanics is a theory about how things evolve through time. At a singularity, time ends. Quantum mechanics has nothing left to stand on, and somewhere between the normal time we experience and the stop time of a singularity, something new must take over. A theory that can handle space and time not as a fixed stage, but as something that can distort, compress, and ultimately break. Finding that theory is the goal. And physicists have proposed a framework so sweeping, so mathematically demanding, so architecturally strange, that it required reinventing the entire picture of what matter and energy are. On September 14th, 2015, two detectors separated by 1,800 miles both shook at the exact same moment. They did not shake in any way you would feel. Each detector is an L-shaped tunnel, each arm 4 kilometers long, a straight line of laser light bouncing back and forth between mirrors. The shaking they detected moved those mirrors by a distance 20 times smaller than a single proton. That signal was a gravitational wave. And the event that created it happened 1.3 billion years ago. Two black holes had been spiraling toward each other for billions of years. Each one was dozens of times more massive than our Sun. As they got closer, they accelerated. They began to move at a significant fraction of the speed of light. The space around them warped violently. And in a final fraction of a second, they merged into a single black hole, releasing more energy in that instant than all the stars in the observable universe produce in a year. That energy did not radiate as light. It radiated as ripples in the fabric of space itself. Einstein had predicted this in 1916, almost exactly a century before it was detected. He showed mathematically that accelerating masses should create waves in space, the same way a boat moving through water creates waves on the surface. These ripples would travel outward at the speed of light, carrying the fingerprint of whatever violent event created them. He also thought they would be far too weak to ever detect. He was nearly right. The Laser Interferometer Gravitational Wave Observatory, a pair of detectors, one in Louisiana and one in Washington state, was built at a cost of over $1 billion specifically to detect these ripples. Its sensitivity is almost incomprehensible. It can measure a change in length equal to 1/10,000th the diameter of a proton across a 4-kilometer tunnel. And it worked. The signal from those two merging black holes, a tiny stretching and squeezing of the Earth itself as the wave passed through, was captured. For the first time in history, humanity directly detected the geometry of space changing. This opened a completely new way to observe the universe. Every telescope before this moment detected light. Gravitational wave detectors sensed the shape of space itself moving. Objects that produced no light, like colliding black holes, became observable for the first time. The universe gained a new voice. But gravitational waves are more than a discovery tool. They are a direct demonstration of general relativity's core claim. Space is a physical thing. It bends, it ripples, it carries energy. The fabric of the universe is real, and it shakes when massive things move through it. Every gravitational wave detection confirms Einstein's framework. Every measurement that matches his equations pushes general relativity further into the territory of settled science. Which makes the failure to combine it with quantum mechanics more baffling, not less. Two confirmed, deeply tested, monumentally precise theories, sitting side by side. Incompatible, the search for a bridge between them led some physicists to a radical idea. An idea that proposed a completely new foundation for what matter itself is made of. A foundation so abstract and mathematically demanding that it took an entire generation of the world's best physicists to develop it. And even after 40 years, it still has not produced a single testable prediction. Particles are the building blocks of matter. That has been the assumption since ancient Greece. Democritus proposed atoms. 20th century physicists found that atoms had nuclei and electrons, that nuclei had protons and neutrons, that protons and neutrons had quarks inside them. At every level, the picture was the same. Smaller pieces. Tinier dots. Points with no size, no internal structure, just properties like mass and charge. String theory said, what if they are not points at all? What if every particle, every quark, every electron, every photon is actually a tiny loop of vibrating energy? A string so small it would take 100 billion of them laid end to end to span the width of a single proton. A string with no thickness, no internal structure, just length and vibration. Different vibrations produce different particles. A string vibrating at one frequency is an electron. The same string vibrating at a different frequency is a quark. Another frequency produces a photon. The strings themselves are identical. The identity of every particle in the universe comes from how its string is vibrating, the way different notes come from the same guitar string depending on how it is plucked. This was proposed in the late 1960s and developed intensively through the 1980s. Physicists were drawn to it for a specific reason. When they wrote down the quantum equations for a vibrating string and worked through the mathematics, a specific vibration pattern appeared automatically. A massless particle with a particular set of properties. When they checked those properties against the hypothetical graviton, the force carrier for gravity, they matched. String theory produced gravity as an automatic consequence. Every other attempt to build a quantum theory of gravity had to force gravity in from the outside. String theory included it by default. The graviton appeared without anyone asking for it. That was startling. To many physicists, it felt like a signal that the theory was onto something deep. The mathematics also showed something else. String theory, to remain consistent, required the universe to have more dimensions than 3 spatial ones. The first fully developed version required 26 dimensions. Later, more refined versions reduced that to 10. With a modification called M-theory, the number rose to 11. 10 or 11 dimensions. Compared to our familiar 3 of length, width, and height. Where are the rest? That question will pull us into one of the strangest ideas physics has ever proposed. An answer that involves geometry so small it has never been observed, and mathematics so abstract that only a handful of people on the planet fully understand it. And the even stranger part is that this might be exactly where gravity is hiding. Picture a garden hose from far away. It looks like a line. One-dimensional, length only. Walk closer and something changes. The hose has a circular cross-section. A second dimension, curled around the length of the tube. From far enough away, you cannot see the circular dimension at all. It is there, but it is too small to notice. String theory uses this same idea. The extra dimensions are real, but curled up so tightly that they are invisible. Each point in our three-dimensional space contains these extra dimensions wrapped into a tiny geometric shape, folded down to roughly the Planck length in size. Far beyond what any microscope can see. Far beyond what any particle accelerator can probe. The shapes these extra dimensions form are called Calabi-Yau manifolds. They are complex six-dimensional geometric structures. You cannot visualize a Calabi-Yau manifold. Most mathematicians who study them understand them only through equations, but the shape of these curled dimensions determines the properties of the particles that strings produce, including their masses and how they interact. This is where string theory becomes both powerful and frustrating. Powerful because the math is consistent, the theory holds together, the graviton appears. Quantum mechanics and gravity coexist in the same framework. String theory is the only known theory that achieves this without producing the catastrophic infinities that destroyed every previous attempt. Frustrating because the number of possible Calabi-Yau shapes is astronomical. Physicists estimate there might be 10 followed by 500 distinct possible shapes, each one producing a different universe with different particles and different physical laws. Some of those universes contain particles like ours, most do not. But string theory provides no rule for picking which shape our universe actually uses. This landscape of possibilities, 10 followed by 500 potential universes each with different physics, is called the string landscape. It has caused enormous controversy. Some physicists see it as a failure. A theory that cannot predict which universe we live in is a theory that describes no universe specifically. A map with 10 followed by 500 destinations, but no pin marking you are here. Others argue this might be telling us something true and strange about reality. If all those universes exist somewhere, and ours is one of them, then the specific physics we observe might be a matter of which universe we happen to occupy. This idea connects to a concept called the multiverse, where countless universes with different physical laws all exist simultaneously. But a prediction about universes you cannot visit cannot be tested, and without testable predictions, string theory sits in an uncomfortable scientific position. The math is extraordinarily beautiful. The structure unifies gravity with quantum mechanics. The landscape is a potential crisis for predictability. After more than 40 years of development and the work of thousands of physicists, string theory has produced 0 confirmed experimental predictions specific to itself. Every test that could distinguish string theory from simpler alternatives has, so far, found nothing. That frustration drove some physicists to go back to basics, to ask whether you could quantize gravity on its own, without bringing all the other forces along, without extra dimensions, without strings. The result was a theory built on a startling image of what space actually is at the deepest level, an image of rings and loops and a universe made of something that resembles a cosmic net. In science, when something shows up by accident, physicists pay attention. Discoveries made while looking for something else have a track record. Penicillin was noticed on a contaminated petri dish. The cosmic microwave background radiation, the leftover glow from the Big Bang, was found while engineers were trying to eliminate noise from a satellite antenna. Accidental discoveries carry a specific weight. They suggest the universe was trying to tell you something. The graviton appeared in string theory by accident. In the late 1960s, a physicist named Gabriele Veneziano was studying the strong nuclear force. He wrote down a mathematical formula to describe how certain particles scatter off each other during high-energy collisions. The formula worked reasonably well. Then other physicists looked deeper into the mathematics and asked what kind of physical object could produce equations with that structure. The answer was a vibrating string, a one-dimensional object with tension vibrating in space. Several physicists developed this idea through the early 1970s. They wrote out the full quantum mechanics of a vibrating string, they calculated all the possible vibration modes, and sitting among the results, one mode did not match any particle in the strong nuclear force. It was massless. It had a spin of 2. Physicists already knew that a force carrier with those exact properties, massless and spin 2, must be the graviton. The equations required by quantum mechanics combined with the theory of relativity leave no other possibility for what a massless spin 2 particle is. The graviton has those properties by mathematical necessity. Nobody had asked string theory to produce a graviton. The graviton appeared anyway. This was a moment that changed theoretical physics. Before this, every attempt to build a quantum theory of gravity was a conscious effort. Physicists took gravity as a target, aimed their equations at it, and watched the math explode into infinities. String theory was built to describe something else entirely. It found the graviton on its own. The implication was serious. String theory might be the correct framework for quantum gravity. It might be the theory that finally bridges the gap. The fact that it contained the graviton without being designed to do so suggested it was capturing something real about the structure of forces. Physicists reoriented the entire research program. String theory stopped being a model for the strong nuclear force and became a candidate theory of everything. A framework that might describe all particles, all forces, all interactions in a single unified language. The mathematics deepened. The theory grew more elaborate and more beautiful. It connected to areas of mathematics that had never before touched physics. String theory generated results in pure mathematics that mathematicians found surprising and important. The exchange went both ways. But the theory also grew harder to test. As physicists developed it, the energy scales required to observe string effects directly crept upward. The strings themselves, being roughly the Planck length in size, would require an accelerator many orders of magnitude more powerful than anything built or imagined to probe them directly. And the landscape problem remained. 10 followed by 500 possible versions of the theory, each producing different physics, with no selection rule. The graviton appearing by accident told physicists string theory was pointing somewhere important. But pointing is different from arriving. The full destination, a complete, testable, predictive theory of quantum gravity, remains out of reach, and the next attempt to reach it came from a completely different direction. From physicists who asked whether you could skip the strings, skip the extra dimensions, and go directly after space itself. String theory went big. Extra dimensions. Vibrating loops of energy smaller than anything imaginable. A mathematical framework so complex it took decades just to map its edges. String theory proposed a radical new foundation for all of matter and all of physics. Loop quantum gravity went in a different direction entirely. Its founders, physicists Abhay Ashtekar, Lee Smolin and Carlo Rovelli, asked a simpler question. String theory tries to unify all 4 forces at once. What if you only tried to quantize gravity? Forget the other forces for now. Forget strings. Just take general relativity, Einstein's theory of curved space, and apply the rules of quantum mechanics directly to the fabric of space itself. What they found changed how some physicists think about the most basic ingredient of reality. Space, in loop quantum gravity, is not smooth. It is not a continuous fabric that stretches and bends like a rubber sheet. Space is made of discrete pieces, tiny chunks with a minimum size roughly at the Planck length. Below that size, space does not exist. There is no smaller distance. Space is quantized the same way energy is quantized in standard quantum mechanics. These chunks of space are not random. They are connected to each other through a network called a spin network. Imagine a vast web of nodes, each node representing a tiny chunk of space connected by links that encode how much area sits between them. The entire three-dimensional space you move through every day is, at the deepest level, a web of these connections. A cosmic mesh of relationships between chunks of quantized space. As time passes, the spin network evolves. The connections shift, nodes merge and split, and the geometry of space changes. This evolving spin network is called a spin foam. Spin foam is loop quantum gravity's version of spacetime at the quantum level. The name loop quantum gravity comes from an early version of the theory where space was described in terms of loops, closed curves threading through the fabric of space. The modern version uses spin networks instead, but the name stuck. What makes this approach compelling is that it takes Einstein seriously in a way string theory does not. General relativity says gravity is geometry. Loop quantum gravity agrees completely. It takes that claim and quantizes the geometry directly. Space curves because of matter. Loop quantum gravity asks what curved space looks like at the smallest level and answers discrete nodes in a network, evolving through time. There are no extra dimensions, no strings, no assumptions about how many spatial dimensions reality has. Loop quantum gravity works in our familiar 3 dimensions of space and 1 of time. It also avoids one of the deepest problems of other approaches. In standard quantum field theory, space is a fixed background. Strings vibrate against that background. But general relativity says the background is not fixed. The background is dynamic. Loop quantum gravity removes the background entirely. Space is not the stage on which physics happens. Space is physics. The relationships between the nodes of the spin network are all that exist. This sounds elegant, and in some ways it is. But loop quantum gravity has a problem that has haunted it for decades, a problem that sits right at the heart of what science requires. It has struggled to make predictions that differ from general relativity in a way that can be tested. 2 theories. 1 problem. Completely different answers. String theory says the universe has 10 or 11 dimensions, and everything is made of vibrating energy loops smaller than anything we can measure. Loop quantum gravity says the universe has 4 dimensions, and space itself is made of discrete quantum chunks connected in a network. Both claim to solve quantum gravity. Both contain the graviton in some form. Both are mathematically consistent. They cannot both be correct descriptions of reality. The rivalry between these 2 approaches has shaped theoretical physics for decades. It is not just a scientific disagreement, it is a philosophical one. The 2 camps have different ideas about what a good theory looks like, what counts as progress, and how much mathematical beauty matters compared to experimental contact. String theorists argue that the sheer mathematical richness of their framework is evidence of depth. String theory has produced results in pure mathematics that mathematicians independently verified as important and true. The theory connects to many different areas of physics in unexpected ways. This internal coherence suggests it is tracking something real. Loop quantum gravity theorists respond that beauty is not truth. A theory must make testable predictions. And loop quantum gravity, they argue, stays closer to established physics. It does not invent extra dimensions that nobody has ever seen. It quantizes what we know exists, which is space and gravity, without adding layers of speculation. The honest answer to which one wins is that neither has won. Neither has lost either. Both remain incomplete. String theory has the graviton, but cannot predict which universe we live in. Loop quantum gravity respects our 4 dimensions, but has struggled to recover the smooth space of general relativity from its network of nodes at large scales. If loop quantum gravity is correct, then at everyday distances, the discrete network of space should look like the smooth, curved space Einstein described. Demonstrating that the smooth picture emerges naturally from the network has been a major technical challenge. String theory also has a numbers problem. When physicists count the possible configurations of string theory, The number of distinct possible universes is effectively beyond astronomical. Picking our universe out of that landscape requires either a selection mechanism nobody has identified or a philosophical framework like the multiverse that makes the prediction untestable. Both theories are in a race to make contact with experiment. The experiments they both point toward require detecting something at the Planck scale, which, as established earlier, is physically out of reach with any technology we can build. Some physicists think the two approaches might not be rivals at all. Deep connections between string theory and loop quantum gravity have been proposed. Some researchers believe both theories might be different limits of a single deeper framework that nobody has found yet. Others believe that the true theory of quantum gravity has not been invented yet. That both string theory and loop quantum gravity are pointing at the answer without quite reaching it. The way Newton's equations pointed at relativity without containing it, both theories agree on one strange thing. They agree that our understanding of what space and time are is fundamentally wrong, and that fixing it will require an idea stranger than either framework has yet produced. One candidate for that stranger idea does not propose a new theory of gravity at all. It proposes that gravity is not a real force in the first place. Temperature is not a fundamental thing. There is no particle of temperature, no field of temperature running through the universe. Temperature is what you get when trillions of atoms are vibrating, bouncing, and colliding. The heat you feel from a fire is not a thing travelling through space. It is the result of countless tiny motions adding up to something your hand can sense. Temperature is emergent. It arises from something deeper. Some physicists now argue that gravity works the same way. The idea is called emergent gravity, and its most developed version was proposed by Dutch physicist Erik Verlinde in 2010. Verlinde argued that gravity is not a fundamental force at all. Gravity is a consequence of something more basic, the behaviour of information at the quantum level. The argument starts with thermodynamics, the science of heat and entropy. Entropy is a measure of disorder. A tidy room has low entropy. The same room, after a hurricane, has high entropy. The second law of thermodynamics says that entropy always increases. Disorder always grows. The universe moves toward its most probable, most disordered state. Verlinde noticed connections between entropy, information, and the equations of gravity. When you calculate how entropy changes near a massive object, the mathematics produces terms that look exactly like gravitational attraction. The pull of gravity, in this framework, is the universe moving toward higher entropy. Objects fall toward each other because that is the direction of increasing disorder. Gravity is the universe being lazy, taking the path toward maximum chaos. This is a radical shift. Instead of gravity being a force mediated by a particle, the graviton, gravity becomes a statistical effect. An average behaviour of vast numbers of quantum bits of information, the same way temperature is an average behaviour of vast numbers of atoms. If Verlinde is right, searching for the graviton is like searching for the particle of temperature. The graviton does not exist because gravity is not a force. It is a shadow of something deeper. The implications cut through everything. General relativity would still be correct as a description of how gravity behaves at large scales, the same way thermodynamics correctly describes heat without knowing anything about atoms. But the underlying reality would be completely different. The fabric of space would not curve because of mass. It would curve because of how information is arranged at the quantum level. Verlinde's framework has attracted serious attention. It makes some predictions that differ from standard gravity at galactic scales, in ways that might help explain why galaxies rotate differently than general relativity predicts, without invoking invisible dark matter. But emergent gravity is still a framework, not a complete theory. Its mathematical foundations are suggestive rather than rigorous. Critics point out that it explains some things but struggles with others. What it does do is crack open a door that most physicists had kept shut. The possibility that gravity is not in the same category as the other forces. that it does not need a quantum version because it was never quantum in the first place. And if gravity emerges from information, then the place where that information lives is not inside space. According to one of the strangest ideas in modern physics, the information that makes up our universe lives on its boundary. Our entire three-dimensional reality might be a projection from somewhere else. Walk into a room. 3 dimensions, left and right, forward and back, up and down. The room has volume. You move through it. Every object in it has depth. This is so obvious that describing it feels pointless. Now consider that all of that, the entire 3-dimensional content of that room, every object, every particle, every interaction, might be completely encoded on the 2-dimensional walls. Every bit of information needed to describe the interior exists on the surface. The interior is real, the walls are real, but the interior is a kind of projection, fully determined by what is written on the boundary. This is the holographic principle. It comes from a discovery about black holes made by physicists Jacob Bekenstein and Stephen Hawking in the 1970s. They calculated the entropy of a black hole, its total information content, and found something unexpected. The entropy was proportional to the surface area of the event horizon, not the volume inside it. For every other object in physics, information content scales with volume. More volume means more possible states, more information. A black hole with twice the volume does not have twice the entropy. It has entropy proportional to its surface area. The information about everything inside the black hole is encoded on the 2-dimensional surface surrounding it. Physicist Gerard Hooft and later Leonard Susskind generalized this into a principle about all of physics. If a black hole's interior information lives on its surface, maybe the same is true of the whole universe. Everything inside a region of space might be fully described by information encoded on the boundary of that region. The 3-dimensional world might be real, the way a hologram on a credit card is real, but the 2-dimensional encoding on the boundary contains everything needed to reconstruct it. Juan Maldacena made this concrete in 1997 with a specific mathematical construction. He showed that a particular theory of gravity in a curved 3-dimensional space is exactly equivalent to a quantum field theory with no gravity living on the 2-dimensional boundary of that space. The two theories describe the same physics from different perspectives. This is called the anti-de Sitter spacetime and conformal field theory correspondence, known as anti-de Sitter or conformal field theory duality. One side has gravity. The other side has quantum field theory without gravity. They are mathematically identical. This duality has become one of the most powerful tools in theoretical physics. Physicists use it to study quantum gravity by doing calculations on the quantum field theory side where the math is more manageable. They use it to study quantum field theory by calculating on the gravity side. The holographic principle suggests that gravity and quantum mechanics are not actually separate. They are two different descriptions of the same underlying reality, seen from different angles. Quantum mechanics lives on the boundary. Gravity lives in the interior. Both are projections of something more fundamental. If this is right, the problem of quantum gravity might dissolve rather than be solved. The question is not how to combine two incompatible theories. The question is how to find the deeper thing that both theories are shadows of. That deeper thing involves information, and the behavior of information inside a black hole has become the sharpest crisis in theoretical physics, because according to quantum mechanics, information can never be destroyed, and black holes seem to destroy everything. Every great physical theory has been tested. Newton's gravity was tested with pendulums and planet orbits. Einstein's relativity was tested with eclipse photos, atomic clocks, and gravitational wave detectors. Quantum mechanics was tested with slits, electrons, and particle colliders that revealed the inner structure of protons. Every theory eventually meets experiment. Quantum gravity has been waiting for its experiment for over 70 years. The problem is energy. Quantum effects at any scale require enough energy to probe that scale. To see the inside of an atom, you need photons with enough energy to interact with electrons. To see the inside of a proton, you need particles accelerated to much higher energies. The pattern holds all the way down. Smaller scales require higher energies. The Planck scale, where quantum gravity effects become undeniable, requires energies so high that they exceed anything in our solar system by an enormous margin. The most powerful particle accelerator ever built, the one beneath France and Switzerland, accelerates protons to energies roughly 100 million billion times lower than what would be needed to probe Planck-scale physics directly. That gap is not a budget problem, it is a physics problem. To bridge that energy gap with a particle accelerator, the machine would need to be roughly 1 light-year in circumference. 1 light-year. The distance light travels in an entire year. The nearest star to Earth is about 4 light-years away. A machine 1/4 of the way to the nearest star just to probe quantum gravity directly. No civilization could build that. No conceivable future technology makes it realistic within any timescale relevant to human history. Physicists have explored indirect routes. Some theories of quantum gravity predict that the speed of light might vary very slightly depending on the energy of the photon carrying it, an effect called Lorentz violation. If true, photons from distant gamma-ray bursts, explosions so powerful they release more energy in seconds than the sun will in its entire lifetime, should show a measurable spread in arrival times. Satellites have looked. So far, no spread. Either Lorentz violation does not exist, or the effect is too small to detect. Some models predict that space at the Planck scale is slightly grainy, like a digital image, and that this graininess would blur images of very distant objects. Astronomers have looked for this blurring. Nothing conclusive has appeared. The experimental window for quantum gravity is not closed. It is just extraordinarily narrow. This leaves theoretical physicists in an unusual position. They are building mathematical frameworks to describe a regime that cannot currently be tested. The guidance that usually comes from experiment, the feedback that tells a theory it is right or wrong, is largely absent. Some physicists find this deeply uncomfortable. Without experimental contact, theory risks becoming pure mathematics dressed in physical language. Ideas can become elegant and internally consistent without being true. Others argue this is a temporary phase, that as experiments become more sensitive and as new windows onto extreme physics open up, quantum gravity will eventually leave detectable fingerprints. The measurement of gravitational waves was once thought impossible. Then it happened. And there is one natural laboratory where quantum gravity effects are forced to exist. A place where no instrument reaches, but where the universe runs the experiment for us every day. Inside every black hole. At every singularity. In every place where space and time end. 1 followed by 40 zeros. That is the ratio between the electromagnetic force and gravity. If the electromagnetic force were a skyscraper 100 stories tall, gravity would be a single atom sitting on the floor of the basement. Every other force in nature, the strong nuclear force, the weak nuclear force, the electromagnetic force, they operate at energies within a few orders of magnitude of each other. They are all in the same rough neighbourhood. Then there is gravity, sitting incomprehensibly far below, operating at a strength so small it might as well be zero at the particle level. This extreme gap is called the hierarchy problem, and it is one of the most disturbing numbers in all of physics. Here is why it disturbs physicists. The standard expectation in quantum field theory is that the bare values of physical quantities before quantum corrections are applied should be close to the corrected values. Quantum effects shift things around, but they should not shift them by enormous amounts unless something specific causes that. The mass of the Higgs boson, the particle responsible for giving other particles their mass, is sensitive to quantum corrections in exactly this way. Without some mechanism carefully controlling those corrections, the Higgs mass should naturally be driven up toward the Planck scale. The Planck mass is roughly 10 million billion times heavier than what the Higgs boson actually weighs. To get the Higgs mass as light as it actually is, quantum corrections must cancel each other with extraordinary precision. The cancellation required is accurate to 1 part in 10, followed by 34 zeros. This level of precision happening by accident is considered deeply unlikely. Something is cancelling those corrections. Physicists suspect new physics is responsible. Supersymmetry was the leading candidate for decades. It proposes that every particle has a partner particle with different quantum properties, and those partner particles provide the cancellation naturally. Supersymmetric partners would solve the hierarchy problem elegantly. The particle accelerator beneath France and Switzerland was in part built to find supersymmetric particles. They have not appeared. The energies where supersymmetry was expected to show up have been fully explored. Nothing was found. Other approaches to the hierarchy problem involve extra dimensions. If gravity propagates not just through our 3 dimensions of space, but through additional hidden dimensions, then the gravity we observe is a weakened echo of a stronger fundamental force. What seems weak to us is actually a diluted version of something much more powerful, spreading its strength across dimensions we cannot see. This is called the large extra dimensions proposal. It predicts that at very short distances, around a millimeter or smaller, gravity should get measurably stronger as it feels the extra dimensions nearby. Experiments have tested this by measuring gravity at short distances with precision instruments. Gravity behaves exactly as expected, down to a tiny fraction of a millimeter. No deviation, no sign of extra dimensions. The extra dimensions, if they exist, are smaller than 1/10 of a millimeter. The hierarchy problem remains unsolved. The gap between gravity and the other forces remains unexplained. And the experimental searches for the mechanisms that would explain it have, so far, come back empty. Something is hiding the answer. And the most dramatic hiding place in the universe is not a dimension or a particle. It might be a boundary. An edge of space from which nothing returns, and everything that crosses it vanishes from the observable universe forever. You live in 3 dimensions. Every direction you can physically move is a combination of 3, left and right, forward and back, up and down. 3 axes, 3 degrees of freedom. Every location in space can be described with 3 numbers, but the equations of physics do not require exactly 3. The mathematics works in any number of dimensions, and some versions of those equations, particularly in string theory, work better or only work at all, with more. The question is where the extra dimensions went. The most intuitive answer goes back to the garden hose from the string theory chapter. A long thin hose looks one-dimensional from far away, because the circular dimension curled around it is too small to see. If extra dimensions are curled up tightly enough, smaller than anything an experiment can probe, they are effectively invisible. String theory requires 6 or 7 extra dimensions curled up at the Planck length. These are the tiny Calabi-Yau shapes mentioned earlier. Because the Planck length is so incredibly small, these dimensions would be undetectable by any foreseeable experiment. But in 1999, 3 physicists named Nima Arkani Hamed, Savas Dimopoulos, and Giardvali proposed something different. What if the extra dimensions are not curled up at the Planck length? What if some of them are large enough, perhaps as large as a millimeter or bigger, but we cannot detect them because ordinary matter is stuck to a 3-dimensional surface? In this picture, everything you are made of, every electron, every quark, every photon, is confined to a 3-dimensional surface called a brane, short for membrane. These particles cannot move off the brane. They are locked to it the way a bead is locked to a wire. The other dimensions exist beyond the brane, but ordinary matter cannot access them. Gravity is different. In most versions of this idea, gravity is not confined to the brane. Gravity spreads through all the dimensions. This gives gravity somewhere to leak. Its strength is diluted across the extra space. What we feel as the extremely weak gravitational force is the weakened remains of a much stronger force that has spread through dimensions we cannot enter. If gravity leaks into extra dimensions, it should get stronger at very short distances, before it has had a chance to spread out. Two objects brought extremely close together should feel a gravitational pull stronger than Newton's or Einstein's equations predict. Physicists built precision experiments to test this by measuring gravitational attraction between small metal spheres separated by fractions of a millimeter. Gravity followed the expected rules down to distances well below a millimeter. No deviation. No sign of extra dimensions at that scale. The extra dimensions, if they exist and contain gravity, must be smaller than 1/10 of a millimeter. The window for detecting this version of large extra dimensions is essentially closed. But extra dimensions at the Planck scale remain possible and untestable. String theory's compact extra dimensions are still on the table. No experiment can rule them out. No experiment can confirm them. The universe may contain dimensions we will never perceive. The search for indirect evidence continues, and one of the most indirect but potentially most powerful sources of that evidence involves the slow death of black holes, a process discovered by Stephen Hawking that has never been directly observed but may hold the key to everything. Black holes were supposed to be permanent. Once matter crossed the event horizon and fell in, it was gone. Forever, the black hole would sit there indefinitely, its gravity holding everything it had ever swallowed, growing slowly as more matter fell in. Nothing escaped. Ever. Then in 1974, Stephen Hawking did a calculation. He applied quantum mechanics to the space just outside the event horizon of a black hole. Quantum mechanics says that empty space is not truly empty. At any point in space, pairs of virtual particles constantly pop into existence and annihilate each other almost instantly. A particle and its antiparticle appear together from the energy of the vacuum, exist for a tiny fraction of a second, then crash back together and disappear. Near a black hole's event horizon, something different can happen. One particle from a virtual pair falls through the horizon into the black hole. Its partner, with no one left to annihilate with, escapes into space as a real particle. The black hole loses a tiny amount of mass to provide the energy for this escape. To a distant observer, the black hole appears to be slowly radiating particles and losing mass. Hawking radiation. A black hole evaporates. Given enough time, an enormous amount of time for large black holes, it shrinks, smaller and smaller, until, in a final explosion of energy, it disappears entirely. This was a landmark moment. It was the first calculation in physics history that genuinely required both general relativity and quantum mechanics simultaneously. General relativity determined the geometry of the event horizon. Quantum mechanics determined the behavior of virtual particles near it. Neither theory alone could produce the result. Hawking radiation was the first glimpse of what quantum gravity might actually look like in practice. But it immediately created a crisis. If a black hole evaporates completely, what happens to everything that fell in? Every particle that ever crossed the horizon carries quantum information. Quantum mechanics has a fundamental law: information cannot be destroyed. The total information content of a system must be conserved over time, even if it gets scrambled beyond recognition. If everything that fell into a black hole is gone, when the black hole evaporates, that information is gone too. Quantum mechanics says that is impossible. Something must carry the information out. Maybe it is encoded in the Hawking radiation, scrambled but present. Maybe it escapes just before the final evaporation. Maybe it survives in some remnant that does not fully disappear. Or maybe quantum mechanics has to be modified to allow information destruction in extreme gravity, which would mean one of the most tested principles in science is wrong. This is the black hole information paradox. It has been the most intensely debated problem at the intersection of gravity and quantum mechanics for 50 years. Hawking himself spent decades on it. He initially believed information was destroyed. Later in life he changed his position and argued it must somehow be preserved in the radiation. The paradox has not been fully resolved. but the attempts to resolve it have produced some of the most creative ideas in recent physics. Ideas about how information is encoded on surfaces, about how space-time itself might be built from quantum entanglement, about whether the interior of a black hole is even a real place at all. The singularity inside that black hole is the next stop, and inside it, physics does not just struggle, physics ends. Imagine dropping a book into a black hole. Every word on every page, every letter, every ink molecule encodes information. The arrangement of atoms in that book is a physical state. Quantum mechanics says the total information content of a physical system is conserved. It can be scrambled, copied, transferred, or rearranged. But the total amount of information in the universe does not change. The book crosses the event horizon. From outside, you watch it slow down, redden, and fade as time dilation stretches the signal reaching you. To the book, nothing special happens at the crossing. It just continues inward. Inside the horizon, gravity pulls the book toward the singularity. The book is torn apart, its atoms separated, its molecules ripped. The matter falls inward. The information, encoded in the arrangement of all those particles, falls with it. The singularity is a wall. Physics ends there. The matter hits the singularity, and the equations produce infinity. The information reaches the singularity, and the equations cannot track it further. Now the black hole slowly evaporates through Hawking radiation. Particle by particle it loses mass. Eventually it is gone. The radiation it emitted is thermal, meaning it carries essentially random, unstructured energy. The information content of that radiation is negligible. The detailed information about the book, about every particle that ever fell in, appears to be gone. Quantum mechanics says this cannot happen. Information cannot be destroyed. This contradiction is the information paradox. Physicists have proposed several resolutions. The most mainstream view, supported by the holographic principle and related mathematics, is that the information is encoded in the Hawking radiation. Every particle emitted by the evaporating black hole carries a tiny imprint of what fell in. The information is scrambled to an extraordinary degree, but it is there. The black hole acts like an incredibly complex encoder, taking everything that falls in and slowly releasing it in a form almost impossible to decode. This view requires that the radiation from a black hole is subtly correlated in ways that carry information. Detecting those correlations directly is far beyond any technology, but the mathematics of the holographic principle strongly suggests the correlations exist. A more radical proposal involves what physicists call firewalls. This idea, proposed in 2012, argued that the event horizon itself must be a wall of high-energy radiation that destroys anything crossing it. Information would be reflected back rather than carried through. The horizon would be a firewall. The firewall argument rests on quantum entanglement. For Hawking radiation to carry information out, the particles being radiated must be entangled with what is inside the black hole. But quantum mechanics places strict limits on how entanglement can be shared. The math suggests that something must break. Either the interior of the black hole is not what general relativity says it is, or Hawking radiation does not carry information, or the rules of quantum entanglement work differently near extreme gravity. The paradox has not been definitively resolved. But physicists now broadly agree that information is preserved even if the mechanism is not fully understood. The resolution, whatever it turns out to be, will require a complete theory of quantum gravity. The deepest version of the paradox lives at the singularity, the place inside the black hole where the book, the atoms, the information all arrive at a point where space and time end. What happens there is the sharpest question in all of physics, and nobody has an answer. The word singularity carries a weight no other word in physics does. In mathematics, a singularity is a point where a function produces an undefined or infinite result. Divide by 0 and you get a singularity. The curve of 1 divided by x shoots off to infinity as x approaches 0. The point itself does not exist in normal arithmetic. In physics, singularities appear when a theory breaks down. When the equations produce infinity, the theory is telling you it has reached its own boundary. The infinity is a flag, a signal that the model has failed and something new is needed. General relativity produces a singularity at the centre of every black hole. The density becomes infinite. The curvature of space becomes infinite. Every physical quantity that can be computed blows up, and the equations, after producing these results, simply stop. Time ends at the singularity. There is no equation in general relativity that describes what happens next, because general relativity has no concept of next once time ends. Physicists do not believe reality actually becomes infinite at the centre of a black hole. Infinity in a physical equation is a sign that the theory is wrong at that point, not that the universe genuinely contains an infinite density of matter. Something real is happening there. Real matter is being compressed. Real energy is accumulating. But the theory we use to describe it fails before it can tell us what that something is. The singularity is not a place in space. It is an edge of space-time, the end point of every world line that crosses the event horizon. Matter falls toward it, time ends at it, and no information about what exists beyond it can reach any observer outside. Every theory of quantum gravity must deal with this. The singularity is unavoidable. It sits at the centre of every black hole, of which the observable universe contains hundreds of billions. It also appears in the equations describing the Big Bang, the moment of maximum density at the start of the universe, where the same breakdown occurs running in reverse. String theory suggests that the singularity might be resolved by the extended nature of strings. A point particle hitting a singularity is destroyed. A string, having finite length, might thread through it differently. Some string theory calculations hint that the singularity can be avoided or replaced with a region of extreme but finite curvature. The details depend on which version of string theory applies and which type of singularity is being considered. Loop quantum gravity gives a more concrete answer. Because space is made of discrete chunks with a minimum size, you cannot compress space to zero volume. The singularity never forms. Instead, as matter is compressed into the black hole, it reaches a maximum density, bounces, and begins to expand again. In this picture, the interior of a black hole might be a new region of spacetime, expanding outward on the other side of what looks like a singularity from our side. Some physicists describe this as a black hole giving birth to a new universe. Our own universe might have originated this way, the bounce of a collapsing region inside a black hole in some larger space. These ideas are speculative. No observation confirms them. The interior of a black hole is causally sealed from the outside. Nothing that falls in can report back. But the singularity problem is not just about black holes. It appears at the beginning of time. And what quantum gravity says about the first moments of the universe is the most sweeping consequence of solving this problem. Physics has a tradition of building complex things from simple pieces. Atoms from protons, neutrons, and electrons. Protons from quarks. Space-time from points and coordinates. Each layer of simplicity revealed something about structure. Causal dynamical triangulation follows this tradition all the way down to space-time itself. The idea comes from a group of physicists including Jan Ambjorn, Renat Lol, and Jerzy Jurkiewicz, who developed it through the 1990s and 2000s. Their approach asks a direct question. If spacetime is a quantum object, and if quantum mechanics is about summing over all possibilities to find what actually happens, then maybe you can build spacetime by summing over all possible spacetime geometries. The technique works like this. Take tiny building blocks, four-dimensional versions of triangles called four simplices, and glue them together into a spacetime. Each configuration of glued simplices is a possible geometry for the universe. Quantum mechanics says you should sum the contributions of all possible geometries to find the actual behavior of spacetime at the quantum level. The word causal in the name is essential. Earlier attempts at this approach, called Euclidean quantum gravity, allowed time to behave like a spatial dimension. The result was space-time that looked nothing like the universe we live in. It crumpled into random fractal structures with no resemblance to smooth three-dimensional space. Causal dynamical triangulation fixes this by enforcing causality. Time must always point in a consistent direction. Causes must come before effects. With this constraint added, the sum over geometries produces space-time that, at large scales, looks like our four-dimensional universe with the right number of dimensions. This was a significant result. The smooth four-dimensional space-time we inhabit emerged from a quantum calculation without being put in by hand. The familiar large-scale structure of the universe appeared as a consequence of the quantum rules plus causality. At small scales, the picture changes dramatically. Below a certain length, the effective dimension of space drops from 3 to roughly 2. Space becomes lower dimensional at the Planck scale. This is a specific, testable prediction, if instruments ever become sensitive enough to probe it. Causal dynamical triangulation does not require extra dimensions. It does not require strings. It works with the dimensions we can observe and asks what spacetime looks like when you apply quantum rules directly to the geometry. The approach has limitations. It is computationally intensive. Summing over all possible spacetime geometries, even with constraints, requires enormous computing power. Getting the detailed physics of particles and forces out of the framework has proven difficult. The theory describes spacetime, but connecting it to the specific particles and interactions of the standard model remains an open challenge. But it represents a different philosophical approach to quantum gravity from both string theory and loop quantum gravity. Instead of starting from particles and asking what mediates gravity, or starting from space and asking what it is made of, causal dynamical triangulation starts from the spacetime itself and asks what quantum rules produce the universe we see. The result is a universe built from simplices, tiny geometric building blocks, assembled according to rules that enforce causality and summed over according to quantum mechanics. Space and time as a construction kit, and with multiple frameworks now pointing at the Planck scale as the key boundary, physicists have tried harder and harder to find any experimental footprint of quantum gravity effects. The results of those searches reveal something about the nature of the problem. The list is long. Experiments looking for Lorentz violation, tiny energy-dependent differences in the speed of light, experiments measuring gravitational attraction at submillimeter distances, searching for deviations from Newton's law, experiments hunting for supersymmetric particles in particle colliders, experiments analysing gamma-ray burst signals for evidence that spacetime is grainy at small scales, experiments searching for microscopic black holes created in high-energy particle collisions, measurements of gravitational waves looking for signatures beyond general relativity, studies of cosmic microwave background radiation, the afterglow of the Big Bang, searching for quantum gravity imprints from the earliest moments of the universe. Every search has returned nothing inconsistent with known physics. This is not failure in the ordinary sense. Null results, experiments that find nothing, are genuinely informative. Each null result rules out a range of theories and forces theorists to revise their models. The absence of Lorentz violation at detectable scales eliminates entire classes of quantum gravity proposals. The absence of supersymmetric particles at energies the accelerator reached means supersymmetry, if it exists, is heavier than expected. But the pattern across all these searches is telling. Quantum gravity effects are hiding at a scale so far below our experimental reach that no probe we have built has come close. The Planck scale requires energies 100 million billion times beyond our best particle accelerator. Current gravitational wave detectors measure with extraordinary sensitivity, but still sit many orders of magnitude above the regime where quantum gravity becomes relevant. The graininess of spacetime predicted by loop quantum gravity, if it exists, would require photon travel times across billions of light years to produce a measurable spread in arrival times, and even then the signal would be barely above the noise floor of current instruments. Some physicists have turned to cosmology for clues. The very early universe, in the first fractions of a second after the Big Bang, was at energies close to the Planck scale. Quantum gravity would have been active then. The patterns in the cosmic microwave background radiation, the slight temperature variations across the sky that encode the density fluctuations of the early universe, might carry imprints of those quantum gravity effects. Measurements of those patterns have become extraordinarily precise. Future telescopes and detectors will push further. Some theoretical models predict specific shapes in those fluctuations that would distinguish quantum gravity effects from purely classical predictions. Whether those signatures are detectable remains unclear. The predictions depend on which theory of quantum gravity is correct, and that is still unknown. The absence of experimental results is the defining feature of quantum gravity as a field. It is a branch of theoretical physics operating almost entirely on mathematical consistency and conceptual coherence rather than experimental guidance. This makes it unusual. It also makes the next breakthrough, when it comes, likely to emerge from an unexpected direction. A place nobody was looking, a measurement designed for a different purpose that accidentally finds something that changes everything. Physics has a history of exactly this, and the measurement that finally breaks open quantum gravity might not be a direct probe of the Planck scale at all. It might come from understanding something more fundamental about what measurement itself means at the quantum level. Quantum mechanics has a strange feature at its foundation. A particle does not have a definite position until you measure it. Before measurement, it exists in a superposition of many possible positions simultaneously. The act of measurement, the interaction with a detector, forces the particle to commit to one definite state. This is called the collapse of the wave function, and it is one of the most debated aspects of quantum mechanics. What counts as a measurement? Any interaction that leaves a record in the environment counts. A photon bouncing off an electron and hitting a detector counts. A particle leaving a track in a cloud chamber counts. Now consider gravity. Gravity responds to mass. Every particle with mass creates a gravitational field. Every quantum particle in a superposition of positions is simultaneously in two or more positions, which means its gravitational field is also simultaneously in two or more states. The gravitational field is in superposition. This creates a profound problem. To measure the gravitational field of a quantum particle, you need something sensitive enough to detect the gravity of a single particle. The gravitational pull of a single electron is so incomprehensibly tiny that no instrument built or imagined can detect it. The gravitational influence of quantum particles is invisible not because of limitations in our technology, but because gravity at the quantum scale is simply too weak to interact with anything we can observe. The measurement problem in quantum gravity has a second layer. General relativity says that space and time are dynamical, shaped by mass and energy. If a quantum particle is in a superposition of positions, space and time are also in a superposition of different geometries. What does it mean to measure time in a superposition of geometries? Does the measurement collapse the geometry? What is the clock ticking against if time itself is in superposition? These questions do not have answers within current theory. They are places where the frameworks simply break down rather than producing wrong answers. There is no equation to write. The concepts themselves stop applying. One intriguing experiment, proposed by physicists Sugato Bose and Vlatko Vedrol, and independently by Chiara Marletto and Vlatko Vedrol, might provide indirect evidence for quantum gravity without reaching the Planck scale. The idea is to take two small but macroscopic masses, place each in a superposition of two positions, and let them interact only through gravity. If gravity is quantum, meaning if it can transmit quantum entanglement, the two masses will become entangled with each other over time. This entanglement could be detected without ever probing the Planck scale. If it appears, it would prove that gravity can create quantum entanglement, which would confirm that gravity is a quantum force, not a classical one. If it does not appear, the interpretation becomes complicated. Either gravity is classical after all, meaning emergent rather than fundamental, or the decoherence of the masses from their environment destroys the entanglement before it can be detected. The experiment is extraordinarily difficult. The masses must be isolated from all vibrations, electromagnetic fields, and thermal noise. Any environmental disturbance destroys the quantum superposition before gravity has time to create entanglement. Physicists believe the experiment is feasible with technology that is within reach over the next decade or two. It would be the first test of whether gravity is genuinely quantum. Not the Planck scale, not the graviton, just the basic question of whether gravity can be quantum at all. The answer would reshape the entire field, and whatever that answer is, it points toward what a successful theory would finally be able to tell us. The universe has a beginning. 13.8 billion years ago, everything that exists was compressed into a state of unimaginable density and temperature. In a fraction of a second, it expanded. Space itself grew from something smaller than a proton to something larger than a galaxy. Particles formed. Forces separated. The universe began its long journey towards stars, planets, and you. This story comes from general relativity applied to cosmology. Run the equations backward in time and space contracts. Temperature rises. Density increases. The equations work perfectly until the very beginning. At the very first moment, the equations hit the same wall as the centre of a black hole. A singularity, infinite density, infinite temperature. The math produces infinity and the theory ends. Physicists call this the Big Bang singularity. And just like the black hole singularity, it is a place where general relativity tells us nothing useful. Something happened at the very beginning. General relativity cannot say what. A complete theory of quantum gravity would change this. Loop quantum gravity's answer is already partially developed. In loop quantum cosmology, the discrete nature of space prevents the singularity from forming. As you run time backward toward the Big Bang, density rises but space cannot compress below the Planck scale. Instead of reaching infinite density, the universe reaches a maximum density, called the Planck density, and then bounces. Before our Big Bang, in this picture, there was a contracting universe. It collapsed to the Planck density, bounced, and began expanding. Our universe is the expanding phase of what loop quantum cosmology calls the Big Bounce. The beginning of our universe was the turnaround point of a previous one. This predicts something. The quantum bounce would leave a specific imprint on the patterns of the cosmic microwave background radiation, the ancient light that fills the universe, produced 380,000 years after the Big Bang. Future measurements of that radiation might reveal this imprint. String theory approaches the Big Bang differently. Some string cosmology models propose that before the Big Bang, the universe was in a high-dimensional state, where all the extra dimensions were large and our three familiar dimensions were small. A transition in that configuration triggered what we see as the Big Bang. The extra dimensions compactified. Our three dimensions expanded. The universe as we know it began. Other models in string theory, related to eternal inflation, suggest that the Big Bang was a local event. Our universe inflated into its current size from a tiny patch within a much larger eternal structure that continues producing universes in other regions. Our Big Bang was one of infinitely many. If a complete theory of quantum gravity could describe what happened in the first fraction of a second, it would answer questions no theory has ever touched. Why did the universe begin with the specific properties it has? Why are the physical constants what they are? Why does the universe have three large spatial dimensions? These questions currently have no scientific answers. They sit beyond the reach of every known theory. A working theory of quantum gravity would be the first tool capable of addressing them. Its predictions about the earliest moments of the universe could be tested against the most precise measurements of the cosmic microwave background. the history of the universe, written in the pattern of light from its infancy, might finally be readable. And if gravity connects to other universes, the story gets stranger still. The multiverse is the most controversial idea in modern physics. It is controversial because it sits at the edge of what science can test. If other universes exist but can never be observed, never influence ours, never send a signal across the boundary, then their existence makes no testable prediction. A theory that predicts something you can never check is scientifically indistinguishable from a theory that predicts nothing. But the connection between gravity, quantum mechanics, and other universes is tighter than it might appear. String theory's landscape problem produces the multiverse almost unavoidably, with something like 10 followed by 500 possible configurations of the extra dimensions, each one producing a universe with different physical laws, and with eternal inflation constantly inflating new bubble universes in different configurations. The multiverse becomes a prediction of the theory, rather than an add-on. String theory, if correct, implies other universes exist. They are not optional. The same logic applies to certain versions of inflation, the rapid expansion phase of the very early universe. Most physicists accept that some form of inflation occurred, supported by the smoothness and flatness of the observable universe. In eternal inflation models, the inflation never fully stops. It continues in different regions, each inflation ending at a different time and producing a bubble universe with potentially different properties. Our observable universe is one bubble. Others exist beyond our cosmic horizon. So far, these other universes are invisible. The question is whether gravity might provide a window. Some models of eternal inflation predict that neighbouring bubble universes occasionally collide. When two bubble universes brush against each other, the collision leaves a mark in the cosmic microwave background radiation. A specific pattern of circular temperature variations, a ring of altered temperature surrounding the point of contact. Physicists have searched for these circular patterns in the cosmic microwave background measurements. Some candidate signals have been identified and studied. None have been confirmed as unambiguous evidence of a bubble collision. The search continues with increasingly precise measurements from newer instruments. The holographic principle opens another potential window. If our universe is a projection from a lower dimensional boundary, and if that boundary connects in some mathematical way to boundaries of other universes, then correlations between the structures of different universes might leave mathematical fingerprints, even if direct observation is impossible. Gravitational wave detectors also point toward this frontier. In some models, the formation of our universe or collisions with other universes would produce a background of gravitational waves pervading all of space. A stochastic background, a faint hiss of gravitational waves from the earliest cosmic events, might carry information about processes that involve regions beyond our observable universe. The Laser Interferometer Space Antenna, a proposed space-based gravitational wave detector, would be sensitive enough to detect such a background from the very early universe. Its data could constrain which cosmological models are viable, including some that involve connections to other universes. None of these approaches promises a definitive proof. The physics of other universes may remain forever indirect, but gravity, as the force that shapes space-time at the largest scales, is the most natural tool for probing the boundary of the observable universe and what lies beyond it. The answer to whether other universes exist might arrive not through a telescope or a particle detector, but through the ripples of space-time itself. And all of this, the graviton search, the Planck scale, the black hole paradoxes, the multiverse, converges on a single conclusion about where physics stands and what solving gravity would actually mean. Physics has walls. Throughout history, each wall looked permanent. The atom was once the final answer for matter. Then the nucleus. Then quarks. Each new wall, when broken, revealed a deeper structure and opened questions nobody had thought to ask before. The wall between gravity and quantum mechanics is different. Every previous wall was broken by experiment. Scientists built new machines, reached new energies, observed new phenomena, and the new data forced the theory to evolve. The wall between gravity and quantum mechanics may be the first wall in physics that cannot be broken by building a bigger machine. The Planck scale is locked away behind an energy barrier that no conceivable accelerator can reach. The graviton is shielded by the physics of black holes from any direct detection. The singularity is sealed inside an event horizon. The extra dimensions, if they exist, are curled up beyond observational reach. This is an entirely new situation for science. Theories must be built and tested differently here. Mathematical consistency, connections to observational cosmology, indirect signatures in gravitational wave backgrounds, quantum entanglement experiments with small masses. These are the tools available, and they are extraordinarily limited compared to the problem they are aimed at. Yet the stakes of solving this problem are higher than any other open question in physics. A working theory of quantum gravity would describe the first fraction of a second of the universe with full accuracy. It would explain whether the Big Bang was a true beginning or a bounce from something before. It would describe the interior of black holes and what happens to information there. It would explain why gravity is so weak. It would tell us whether extra dimensions exist. It would either confirm the graviton or show that gravity is emergent and the graviton is a concept that does not apply. And it would complete the description of reality. Right now, our understanding of the universe has a gaping structural hole. Two of the most successful theories ever built cannot coexist in the same calculation. Every physicist alive knows this. Every calculation that involves both gravity and quantum mechanics at the same time produces nonsense. The fundamental description of reality is broken. The history of physics suggests that when two successful theories conflict, the resolution always reveals something deeper than either theory contained. Newton's mechanics and Maxwell's electrodynamics conflicted over the behaviour of light, and the resolution was special relativity, which revealed the unification of space and time. Special relativity and Newtonian gravity conflicted, and the resolution was general relativity, which revealed that gravity is geometry. General relativity and quantum mechanics conflict, and the resolution is quantum gravity. What it will reveal, what new layer of reality it will expose, is unknown. But if the historical pattern holds, it will be something that changes the entire framework. Something that makes the current conflict look like a symptom of a misunderstanding so fundamental that physicists will wonder how they missed it. The question of gravity is the question of what space and time actually are at the deepest level. It is the question of whether information is the foundation of reality. It is the question of whether the universe has other versions of itself. It is the question of how everything began. Gravity refuses to fit, because the box it is being asked to fit into is too small. The real theory of everything needs a bigger box. A box that contains ideas nobody has thought of yet. And somewhere, right now, someone might be thinking of them.